Hey, welcome back to maths. Good to be here again to teach you from Compass. Alrighty, hey, yeah, we need to have a chat about selections. Yep. So the other day we looked at arrangements, also known as permutations. This time we need to take it further and have the chat about selections. So again, let's have a look at this particular example of the three letters. Yep. So let's consider the letters A, B, and C when taken in groups of two. So we saw that if you place them in groups of two, there were 6 different arrangements for that. Yep. However, when we start talking about unique or distinct selections, we're not talking about we're just talking about the combination together. We're not talking about the order as being important. So for example, where you've got A and B, they're together, it's the same as having B and A. Yep, so it's just making sure that they are grouped together. So you can have A and B is the same as B and A. Likewise, A and C is the same as C and A. Likewise here, B and C being together. There's only 3 distinct selections in this particular case. So when you start reading these questions outside of these chapters, you need to be thinking, are they asking for the arrangements, all the different ways in which they can be arranged, where the order is important? Or are they asking just what's the chances of people or items being together? It's like really if you were thinking, okay, I'm in the maths class and I'm going to group students together to work on an activity. If I group together Bill and Tom, it's the same as grouping Tom and Bill together. Yep, it doesn't matter the order, they're still a group themselves. All right, so let's have a look here at worked example number 11. Oh, it's the ice cream question. Excellent. I like ice cream. It says here, you've got 4 flavors of ice cream. Vanilla, chocolate, strawberry, and caramel. Okay. Now, and it looks like you can get these from the canteen. That's a pretty cool canteen. It says how many different double scoop selections are possible if 2 different flavors must be used. Okay, so if we think about an ice cream, 2 scoops, there's 2 selections. Ultimately, it doesn't really matter whether you get the first flavor put on the bottom or on the top, you're still getting those 2 flavors. So let's have a look here at the possibilities. Yeah, you could have the vanilla and it could be with the chocolate. They've listed that there. You could have the vanilla and the strawberry. They've listed that there. You could have the vanilla and the caramel. That's been listed there. Perfect. You could also have the chocolate with the strawberry. You could have the chocolate with the caramel. Perfect. And last but not least, you could have the strawberry and the caramel. Okay. Now, we don't need to list back the other way. You don't need to list, okay, chocolate and vanilla. That's already listed here in this other combination there. So it's important to know that's a difference between the arrangements and selections there. Cool. I'll just delete all that. That's a bit messy. Yeah, not deleting. All right. Cool. Let's have a look at this a bit further. So when we're talking about the example, as I suggested, vanilla and chocolate is the same as chocolate and vanilla. Happy days. We spoke about that. As you know, when we have this particular case, without regards to the order, so it doesn't matter which order they're in, these are known as selections or combinations. Now the cool thing is we start denoting this in maths with the NCR terminology, which is the combination terminology. The other day I showed you in the advanced tab of our calculators where factorial symbol was, the exclamation mark, but not in maths, it's the factorial symbol. And I've also spoke about where NPR was, where permutations for the arrangements. For this particular exercise, you'll find the NCR, the combination button, right next to that in that menu, the advanced menu. So again, with these things, the number of different ways in which the group or size, the sizes are, this value can be chosen from a total number of objects. The n is how many objects they can be chosen from. It says when the group size is not large, the combination can be listed. What they're talking about here is referring back to this Olympic flag question that we had the chat about the other day. And so the Olympic flag, it says, suppose that the 5 colours to be used are chosen, and then they are arranged on the flag. In this particular case, you're going to have 8C5. There are 8 colours, and you're choosing 5 of them. Again, if you had to arrange them, you would multiply that by 5 factorial. And in that particular case, you're going to have 8 factorial over 3 factorial as the possible arrangements, which we saw the other day. What they're doing is they're building this up and showing that in this particular case, because 8CR multiplied by 5 factorial is equal to 8 factorial divided by 3 factorial, what you can do is you can find an expression for 8C5 by dividing both sides by 5 factorial, dividing that side by 5 let me get my texter here. By dividing this side by 5 factorial and also dividing this side by 5 factorial, which goes on the line, you end up with this here. Now, what that builds into, it illustrates how all of these things are linked together. So here is the bubble box of fun that you need to have an understanding of. If you've got NCR, so a number of combinations, that can also be represented by NPR, which we did the other way, or the other day, which was the number of arrangements, divided by R factorial. These are the same thing here. The other day we spoke about what NPR is. This is on the top line here. Obviously it's the same as writing this on the bottom line here, R factorial there. Also, building this even further, if you have number of combinations, it's equal to n factorial on the top line divided by r factorial multiplied by, that's a multiplied by, n take away r factorial, and that'll come in useful with the next example. Sometimes in maths you see things a little bit differently. One of the different ways in which, what happened here? One of the different ways in which you can write NCR is just if you have it in brackets and an N and an R, that's just another notation for combinations. So that might pop up in the book. If you see that in the textbook and they're asking to calculate this here, you just know that you're working out NCR. Cool. All right, what's happening? Oh, it's the ice creams are back. It says here, consider the situation from example number 11 again. If the 4 flavors of ice cream are available, how many double scoop selections are possible if 2 different flavors must be used? Okay, so here we've got 4 different choices as the n value. There's n objects. 4 different flavors, and we have a size of 2 have to be chosen, so the R value is 2. Now you could just plug this into your calculator and do 4C2. It will tell you it's 6. If you don't have a calculator, you can apply this rule that's up here. So we know that NCR is the same as this here. So in this case, n factorial, we had n, in this case, imagine I wrote n then. N was equal to 4, and R, imagine that's an R, was equal to a 2. So in this particular case, plugging these values in here, you're going to have 4 factorial on the top line. On the bottom line of the fraction, you're going to have R factorial, which was 2 factorial, and that's going to be multiplied by n take away R. In our case, n take away R is 4 take away 2 is 2 factorial. So that's where that comes from. It's from that rule up there. Now, again, you need to remember what factorial means if you're doing it by hand. 4 factorial means 4 times 3 times 2 times 1. You've got 2 factorial is 2 times 1, and then you've got 2 factorial again, which means times 2 times 1 again on the bottom line. Now, you can do some simplifying with this. That will cancel out there, that'll cancel out there, and you should be able to do this calculation in your head. You've got 4 times 3 on the top line, which is 12. 12 divided by 2 times 1, which is 2, is 6. Cool. So you don't need your calculator to do this. You can work it out using your brain. Cool. Let's have a look at the next one. Oh, It's just sometimes they're not always so straightforward, so you have to do some thinking. We can do that. It says here, example number 13. A team of 3 boys and 3 girls is chosen from a group of 8 boys and 5 girls. How many different teams are possible? All right, so the trick with this one is dealing with the groups. So there's actually, the end value for the boys is there's 8 and they're choosing 3. So for that part, for the boys to calculate it, you would be doing 8C3. Yep, 8 for the combination. There's 8 choices, or sorry, 8 objects, and you're choosing 3. Yep. So that's how you get the 8C3 there. For the girls to work out the possibilities, there's 5 objects in total. There's 5 girls, and we're choosing 3. So in that case, it's 5C3. If you then want to obviously work out how many different teams are possible, you are multiplying the solutions to each of these. So we've got 8C3 multiplied by the girls, which was 5C3. Each of those, that's 56. This one here is 10. We can multiply that together. There are 560 possible teams for that. Oh, cool. You can do some sort of like counting and of selections of any size. It says here, the following result is useful when asked to count all the accommodations of any size from group of n objects. So if you've got a certain amount of objects, n objects, what you do is you're going to have whatever that number is, C0 plus whatever that number is, C1, and so forth until you get to whatever that number is, C that number. And regardless of how many objects there are, it could be 7, 10, whatever, if you add all of those together, it, based on this rule, is equal to 2 to the power of however many objects there are. Now, this is a good one to remember. We'll look at that in more detail in a moment with one of the examples. But really, if you want to know how this rule comes about, this bit of information really illustrates it. I'm happy for you to have a read through that a little bit later. Let's have a look at this last example. Oh, Nick's having a party. Cool. Now, he has 7 friends to choose from. It's going to be this party. It says here, if he may choose to invite any number of friends, that is from 1 to all the 7, how many party lists is he going to have? Note, it's assuming he's having a party with at least one person. He's not having a party by himself, okay? Good to note that one there. All right, so it says here, Nick may invite one person to the party. In that particular case, if he's inviting one person to the party, out of 7 objects and choosing one, it's going to be 7C1, which is 7 ways of doing this. You could then go ahead and work out the same if he invites 2 people to the party. It's 7C2, there's 21 ways of doing that. If you did that, 7C3 and so forth, you could get all the different ways in which he's going to invite the people to his party. So you essentially would be adding each of those together, which can be done. If you were to work that out, you'd get that this is equal to 127. That's all the different possibilities there. The other way you could calculate this, if you didn't have a calculator, you couldn't be bothered working all this out, you could go, okay, if you know that based on this rule up here, the total number of combinations for n objects, in our case it's 7, is going to be equal to all of those added together, it's 2 to the power of 7. Yeah. So 2 to the power of 7 is 128. Imagine that's a 128. Yep, and that's just because there's 7 objects to choose from. Total arrangements is combination. Is 2 to the power of 7. But he has to have at least one person, so you're going to subtract that option away from there. So 2 to the power of 7, take away 7C0, so when he's got no choices, because that wasn't one of the parts, he has to have at least one person to his party. 7C0 is 1, so you could have calculated it, rather than adding up each of these, just doing 2 to the power of 7, take away this one here, which is 1, gives you the 127 there for that. Cool. Thank you very much for listening. I'm going to put this exercise's PDF up online. It'd be really good if you could have a bit of a go of this. I realize textbooks likely not at home. Hopefully you do have a piece of paper and a pen at home to have a go of this. Good luck. Take care for now. Bye.